the universe is vast, ancient, and filled with enigmas that continue to defy explanation. From the deepest cosmic voids to the brightest stellar explosions, mysteries lie hidden within the very fabric of space and time. While science has illuminated many aspects of the cosmos, certain discoveries remain unresolved, suspended between evidence and speculation. They remind us that the universe is far greater than our current understanding and may conceal truths yet unimaginable. These unsolved discoveries are not merely unanswered questions, they are doorways to new realms of possibility, shaping the very path of exploration. With that said, let us begin. Among the most perplexing discoveries of the cosmos is the elusive substance known as dark matter. It is invisible to every instrument that relies on light, yet its presence is undeniable. Galaxies rotate with a speed that cannot be explained by the gravity of visible stars alone. If only ordinary matter existed, galaxies would fling themselves apart, their stars scattering into the void. But they remain bound, spinning in patterns that betray the pull of something unseen. Astronomers noticed these discrepancies decades ago, while studying the motions of stars in the outer arms of spiral galaxies. The stars moved too quickly, as if some vast, hidden mass held them in place. This hidden mass, now called dark matter, is thought to make up about 85% of all matter in the universe. Yet it cannot be touched, detected directly, or captured in any laboratory experiment with certainty. Some theories suggest it consists of exotic particles, far beyond the known elements of the periodic table. Others propose vast halos of unseen objects, or entirely new forces woven into the cosmic fabric. Whatever its nature, dark matter surrounds galaxies like invisible scaffolding, shaping their formation and evolution. Without it, the large-scale structure of the universe, the cosmic web of filaments and voids, could never have formed in the way it has. Still, despite countless experiments and detectors buried deep underground, dark matter has never revealed its true form. It is there, exerting gravity, sculpting galaxies, yet forever hiding in shadow. The question remains, what is this mysterious substance, and why does it refuse to show its face to us? In the late 20th century, a discovery shook the foundations of cosmology. By observing distant supernovae, scientists expected to confirm that the universe's expansion was slowing, dragged down by the pull of gravity. Instead, they found the opposite: the expansion is accelerating. Galaxies are not just drifting apart. They are racing away faster and faster, as if driven by an invisible hand. This acceleration implies the presence of another unseen phenomenon, now called dark energy. Unlike dark matter, which binds, dark energy repels. It appears to stretch space itself, overwhelming the force of gravity on the largest scales. Calculations suggest that nearly 70% of the universe consists of this enigmatic energy, yet no one knows what it truly is. Some describe it as a property of space itself, a constant push embedded within the fabric of the cosmos. Others see it as evidence of unknown fields or new dimensions beyond comprehension. The acceleration raises profound questions: will the universe expand forever, tearing galaxies, stars, and eventually atoms apart in a big rip? Or will dark energy shift in strength, changing the ultimate fate of everything that exists? This discovery redefined our picture of the cosmos. Instead of slowing down, the universe is rushing toward an uncertain destiny, carried forward by a force that cannot be measured directly. It remains one of the greatest unsolved discoveries, a cosmic engine without a known fuel. Scattered across the night sky, far beyond the reach of any telescope's detailed vision, are signals that defy understanding. In the early 2000s, astronomers detected sudden, intense bursts of radio waves, lasting only milliseconds, yet releasing more energy than the sun emits in days. These events, known as fast radio bursts, or FRBs, appear without warning, vanish instantly, and often never repeat. Their origin remains uncertain. Some come from galaxies billions of light-years away, their signals stretched and distorted by the vastness of intergalactic space. Others occur closer, perhaps within our own cosmic neighborhood. Theories range from the collapse of exotic stars, to magnetars unleashing colossal flares, to interactions of matter with black holes. More speculative ideas suggest they may be signatures of phenomena entirely outside known physics. A few FRBs have been observed repeating, offering astronomers a chance to study them in greater detail. These repeating bursts challenge the idea that they are one-time cataclysmic events, hinting at a mechanism capable of producing multiple explosions without destroying the source. Yet even with improved instruments, no definitive explanation has emerged. The sheer energy and brevity of FRBs make them one of the most mysterious discoveries in astronomy. They remind us that the universe is still full of surprises, where even the emptiest stretches of space can erupt with power beyond imagination. In the depths of intergalactic space, there exists a gravitational anomaly so vast that it pulls entire galaxies toward it. Known as the Great Attractor, this unseen concentration of mass lies hundreds of millions of light years away, hidden behind the thick plane of our own Milky Way. Galaxies in our region, including our own, drift toward it with astonishing speed, as if caught in the grip of a cosmic current. The discovery came from mapping galactic motions. Astronomers expected galaxies to move more or less evenly, expanding outward with the universe. Yet many were flowing in the same direction, as though drawn toward an immense, hidden anchor point. Calculations revealed this attractor's mass is incomprehensible, on the order of tens of thousands of Milky Way galaxies combined. What is it? Some propose that the Great Attractor is not a single object, but a vast region dominated by clusters of galaxies, dark matter, and superclusters all merging into one gravitational basin. Others speculate it could connect to larger structures, like the Laniakea supercluster, which encompasses our Milky Way and stretches across unimaginable expanses. Yet its exact nature remains obscured. The dense dust and stars of our galaxy block clear observation, making it one of the most difficult regions of the sky to study. Hidden behind this zone of avoidance, the Great Attractor lingers like a shadowy presence, felt but not seen. We move inexorably toward it, carried on a current whose destination is unknown, reminding us that even the largest maps of the cosmos may be incomplete. Few discoveries have inspired both fascination and fear like black holes. Predicted by the equations of general relativity, they represent regions of space where gravity becomes so intense that not even light can escape. Yet beyond their boundaries, the event horizon, lies an enduring mystery. What happens inside? Observations show black holes exist in many sizes, from stellar remnants a few times more massive than the Sun, to supermassive giants anchoring galaxies with billions of solar masses. Their existence is confirmed through their effects. Stars orbiting invisible companions, gas heating as it spirals inward, and in rare cases, the shadowy outline of the event horizon itself. But the inner structure remains unknown. Do black holes contain singularities, infinitely dense points where the known laws of physics collapse? Or do they hide exotic cores, governed by physics we have yet to discover? Some theories suggest the existence of wormholes, linking distant regions of space and time. Others propose that black holes could evaporate over immense timescales, releasing information in ways not yet understood. The paradox of information loss, whether matter consumed by a black hole is gone forever or somehow preserved, remains one of the deepest unresolved puzzles in science. Each black hole is both a laboratory of extreme physics and a wall beyond which no signals return. They are cosmic riddles, existing not just as collapsed stars, but as questions about the very limits of reality. When the cosmic microwave background. The faint afterglow of the Big Bang was mapped in exquisite detail. Astronomers notice something unusual. Amid the nearly uniform sea of ancient radiation lies a region that is colder and emptier than expected, the so-called cold spot. This anomaly, spanning hundreds of millions of light years, is significantly larger and darker than typical fluctuations in the cosmic background. It has sparked intense debate about its origin. Could it be a statistical fluke, a rare alignment of random variations? Or does it point to something extraordinary lurking in the structure of the universe? One idea suggests that the cold spot is caused by a vast supervoid, a region of space with fewer galaxies than average. Light passing through such a void would lose energy, leaving behind a cooler patch. But even this explanation struggles to account for the full scale of the anomaly. More speculative theories hint at something even stranger. That the cold spot may be evidence of contact with another universe, a scar from a collision with a neighboring cosmos in a larger multiverse. If true, this would represent one of the most profound discoveries ever made, though the evidence remains far from conclusive. The cold spot remains unsolved, an enigmatic blemish on the map of the earliest light, a whisper from the dawn of time that refuses to be explained. When astronomers measure the composition of the universe, they find something puzzling. The amount of ordinary matter, atoms, protons, neutrons, and electrons, doesn't match predictions. By studying the early universe, particularly the light elements forged in the first minutes after the Big Bang, scientists can estimate how much baryonic matter should exist. Yet when they look around today, only about half of it is accounted for. The rest appears to be missing. This puzzle is not about dark matter, but about the normal matter we understand. Stars, planets, and galaxies represent only a portion of what should be present. Where is the rest? After decades of searching, some clues have emerged. Astronomers have found faint traces of matter in the form of diffuse gas, spread thinly across the cosmic web. This gas, heated to extreme temperatures, emits only weak signals, nearly impossible to detect. New observations suggest that these missing baryons may exist in filaments stretching between galaxies, woven into the vast structures of the universe. Using techniques such as the Sunyarev-Zeldovich effect, scientists have glimpsed signs of this elusive matter. But even these detections are incomplete, leaving uncertainty about whether the entire deficit is explained. The missing baryon problem reminds us that even the matter making up stars and planets, things we assume we understand, can slip from view when stretched across the enormity of space. It is a cosmic accounting error that still awaits a final resolution. Quasars are among the most luminous objects in the cosmos, powered by supermassive black holes devouring matter at the centers of galaxies. Their light shines across billions of light years, reaching us from the distant past. Yet in their distribution lies a mystery that challenges assumptions about cosmic uniformity. Studies have revealed that certain quasars, separated by unimaginable distances, appear to align with one another. Their polarization, the orientation of their light waves, points in similar directions, as though synchronized across billions of light years. This alignment stretches far beyond the scale where any local interaction should be possible. Why would quasars, scattered across the observable universe, display such coherence? Some suggest this may point to unknown large-scale structures of space itself, perhaps patterns woven into the cosmic web. Others consider the possibility that these alignments are statistical coincidences, though the likelihood of such chance is debated. If real, the alignment of quasars may suggest that the universe is not as isotropic as once believed. It could hint at hidden physics influencing the orientation of galaxies and black holes on cosmic scales. The mystery deepens with each survey, as new data confirms that these strange alignments persist, whispering of forces or principles that remain concealed. In 1977, a powerful and unexplained signal was detected by the Big Ear radio telescope in Ohio. Lasting just 72 seconds, it was so striking that the astronomer on duty, Jerry Ehrman, circled it on the computer printout and wrote "WOW" in the margin. Since then, it has been known simply as the WOW signal. The signal came from the constellation Sagittarius, near the direction of the galactic center. It bore the expected hallmarks of an artificial transmission. A narrowband spike at 1420 MHz, a frequency associated with neutral hydrogen, the most abundant element in the universe. If an advanced civilization wanted to send a beacon, this would be a logical channel. Yet despite follow-up searches, the signal has never repeated. Some explanations suggest it could have been caused by Earth-based interference, though none fit perfectly. Others speculate about comets or natural phenomena producing radio emissions, but no consensus has been reached. The WOW signal remains one of the strongest candidates for a potential extraterrestrial message, though its origin is unresolved. It is a reminder of how, amid the vast static of the cosmos, a single unexplained whisper can ignite imagination and leave us questioning whether we are alone. From the depths of the universe, particles rain upon Earth at near-light speeds. Most cosmic rays are well understood, produced by supernovae or stellar processes. But among them, a rare few arrive with energies so extreme that they defy explanation. These are the ultra-high-energy cosmic rays, particles with energies millions of times greater than what human-built accelerators like the Large Hadron Collider can achieve. The origins of these cosmic bullets remain unknown. Their energies are so immense that they cannot have traveled very far, as they would interact with cosmic background radiation and lose momentum. Yet their arrival directions show no clear nearby sources. No local supernova or galaxy seems capable of accelerating them to such extremes. Some theories suggest active galactic nuclei or the shockwaves of colliding galaxy clusters could hurl particles to these energies. Others look to more exotic possibilities, such as the decay of primordial particles left over from the early universe, or even the influence of topological defects in spacetime itself. When one of these cosmic rays strikes Earth's atmosphere, it creates a cascade of secondary particles, detectable by vast ground arrays and observatories. Yet despite decades of study, their origin story remains elusive. Each ultra-high-energy particle is a messenger from the unknown, a hint of processes in the universe far more powerful than anything understood today. In 2015, astronomers noticed something strange in the light of a star located about 1,500 light-years away in the constellation Cygnus. Unlike other stars that dim periodically due to orbiting planets, this star, and now famous as Tabby's star, flickered in irregular and dramatic ways. Its brightness dropped by as much as 20% in a manner no planet could explain. The discovery sparked worldwide fascination. Some speculated about vast alien megastructures, so-called Dyson swarms, blocking the light. Others suggested enormous clouds of dust, swarms of comets, or unknown astrophysical processes at work. The star's behavior was so unusual that none of the typical explanations fit comfortably. Long-term observations revealed that Tabby's star also appears to be dimming over decades, further complicating the mystery. No known stellar process matches this gradual fading combined with sudden, irregular dips. The current leading explanation points toward clouds of fine dust or complex circumstellar material, but even this does not account for every observed pattern. The truth remains uncertain, and Tabby's star continues to stand as one of the strangest stellar puzzles ever recorded. Its unusual behavior is a reminder that even familiar stars can harbor phenomena beyond understanding. Among the greatest unsolved discoveries of the universe is not a distant galaxy or a faint signal, but something woven into the experience of existence itself, time. While space can be measured in length, width, and height, time remains both fundamental and elusive. It flows forward, carrying every star, planet, and atom with it. Yet its true nature remains undefined. On cosmic scales, time appears relative. The faster one moves, or the closer one approaches a gravitational source, the more slowly time passes. This has been observed with astonishing precision even in clocks flown on airplanes or satellites. Time is not universal, it bends and stretches depending on context. Yet why time seems to flow in one direction, from past to future, is an unsolved mystery. The equations of physics work equally well forward or backward, yet reality seems to prefer a single path. This arrow of time may be tied to entropy, the gradual increase of disorder, but the ultimate reason remains unresolved. Even deeper mysteries linger. Is time a fundamental property of the universe, or an emergent feature arising from deeper laws not yet uncovered? Could it behave differently in regions beyond the observable cosmos? And at the edge of black holes or at the birth of the universe, does time itself dissolve into something else entirely? Time is both intimate and alien, the stage upon which all cosmic dramas unfold, and yet one of the universe's most unsolved discoveries. Among the strangest stars in the universe are magnetars, neutron stars with magnetic fields so intense they defy comprehension. A single teaspoon of their matter would outweigh mountains, yet it is their magnetism that sets them apart. These fields are trillions of times stronger than Earth's, powerful enough to strip electrons from atoms across vast distances. Magnetars occasionally unleash bursts of energy so violent they can outshine entire galaxies for brief moments. In 2004, a giant flare from a magnetar within our galaxy disrupted satellites and ionized Earth's upper atmosphere, despite occurring tens of thousands of light-years away. Such events suggest these objects are not only powerful but volatile, capable of reshaping their surroundings with every eruption. Yet the mystery remains: why do only some neutron stars become magnetars? The exact process that generates such fields is uncertain. Some theories propose that a rapid rotation at birth winds magnetic fields to extremes, while others suggest exotic states of matter within their cores. Even more puzzling is their lifespan. Magnetars seem to be short-lived, fading within just a few thousand years, mere instants on cosmic timescales. If so, the fact that we observe them at all may be a remarkable coincidence. The question persists: what deeper forces create and govern these magnetic titans, and what role might they play in shaping the galaxy? The observable universe contains hundreds of billions of galaxies, each filled with countless stars and planets. By simple probability, life should exist elsewhere, perhaps even intelligent civilizations capable of communication. Yet despite decades of searching, from radio telescopes scanning the skies to probes exploring nearby worlds, there is only silence. This contradiction is known as the Fermi paradox. If life is common, where is everyone? Why has no signal, no evidence, no unmistakable sign of extraterrestrial technology appeared? Some explanations suggest that civilizations are rare, fragile, or short-lived, extinguished before they can reach the stars. Others argue that advanced beings might deliberately remain hidden, avoiding contact. Still others propose that life could be everywhere, but in forms so alien that we fail to recognize it. Perhaps intelligence does not always manifest in ways familiar to us, perhaps it dwells in oceans of methane, in plasma clouds, or in states of matter beyond comprehension. The paradox is sharpened by discoveries of exoplanets. Many orbit in habitable zones, where liquid water could exist. The conditions for life appear common, not rare. And yet the silence persists. Until the paradox is resolved, it stands as one of the greatest unsolved discoveries of the universe, the absence of voices in a cosmos that should be filled with them. Across the sky, brief flashes of energy erupt with unimaginable force. Gamma-ray bursts, lasting from fractions of a second to several minutes, release more energy than the sun will emit in its entire lifetime. First discovered in the 1960s by satellites monitoring nuclear activity, these bursts turned out to be cosmic in origin, coming from far beyond our galaxy. There are two main classes, long bursts and short bursts. Long bursts are thought to be linked to the collapse of massive stars, producing hypernovae and black holes. Short bursts may arise from the collisions of neutron stars, releasing titanic amounts of energy in moments. Yet even with these models, mysteries remain. Some gamma-ray bursts defy classification, lasting longer than expected, or showing unusual afterglows. Others seem too powerful to be explained by known processes. Their incredible brightness allows them to be seen across billions of light-years, making them useful probes of the distant universe. But at their core, the exact mechanics of how such intense energy is concentrated and released remain uncertain. These bursts are both terrifying and illuminating, windows into extreme physics. They remind us that the universe is not a quiet place, but a stage where titanic explosions can reshape galaxies and challenge the limits of our understanding. Not every world belongs to a star. Drifting silently through the galaxy are rogue planets, worlds cast adrift, wandering without the warmth or light of a sun. They are thought to form in planetary systems like our own, only to be ejected through violent gravitational encounters. Others may form directly from collapsing clouds of gas, like failed stars. These planets are almost invisible, for without reflected starlight they vanish into the blackness of space. Yet surveys using gravitational microlensing, where a planet's gravity bends and magnifies the light of a distant star, have revealed their presence. Some estimates suggest there could be more rogue planets than stars in the Milky Way, an unimaginable population of cold, dark worlds. What might such planets be like? Some may carry frozen oceans, others molten cores that keep subterranean heat alive for billions of years. Concealed beneath thick layers of ice, they could even harbor life, warmed not by starlight but by geothermal energy. The discovery of rogue planets challenges the view of planets as mere companions to stars. Instead, they are independent wanderers, shaping the galactic landscape in ways we are only beginning to understand. Each rogue world is an unsolved discovery, a reminder that entire planets can exist in perpetual exile, hidden within the endless night. In the 1970s, the Pioneer 10 and Pioneer 11 spacecraft were launched on trajectories that carried them beyond the outer planets, into interstellar space. As they traveled, precise tracking revealed something unexpected. A tiny but consistent deviation in their motions. They were slowing slightly more than calculations predicted, as if tugged by an unknown force. This became known as the Pioneer anomaly. For years, it puzzled scientists. Could it be the pull of unseen mass in the solar system? A modification of the laws of gravity at large distances? Or even a sign of something new in the physics of space itself? Careful reanalysis eventually suggested that heat emitted by the spacecraft's instruments and radioisotope generators could account for most of the effect. But the explanation remains debated. Some researchers accept the thermal recoil theory, while others argue subtle discrepancies persist. The Pioneer anomaly reminds us of the razor-thin precision required in exploring the cosmos. Even the faintest deviation can spark questions about the laws that govern motion across the universe. Though perhaps not as dramatic as dark matter or black holes, it stands as a testament to the fact that even small spacecraft, slipping quietly into the stars, can uncover mysteries still unresolved. When astronomers map the orientation of galaxies across the sky, they encounter a strange puzzle. Galaxies spin either clockwise or counterclockwise, depending on the observer's perspective. By cosmic logic, these orientations should be randomly distributed. Yet surveys have hinted at patterns, large regions where spins appear to align, as though the universe itself has a preferred direction. If true, this would challenge the cosmological principle, the idea that, on large scales, the universe is isotropic and without bias. Instead, it would suggest that vast cosmic structures may rotate in unison, connected by mechanisms unknown. Some propose that primordial conditions after the Big Bang imprinted this pattern, or that the large-scale cosmic web may guide spins through tidal forces. Others suspect that observational bias may influence the data, and that the patterns could be illusions of incomplete sampling. Still, the possibility remains intriguing. If galaxies truly share a preferred spin orientation, it may point toward new physics, hidden symmetries, or forces extending across billions of light years. The very act of galaxies turning, spirals etched into the night sky, may carry clues about the deepest architecture of the cosmos. In 1989, when the Voyager 2 spacecraft flew past Neptune, it captured images of a massive storm unlike anything seen before, a vast dark spot spinning across the planet's atmosphere. Similar to Jupiter's Great Red Spot, this storm appeared as a swirling vortex, but with key differences. It seemed to form and vanish on timescales far shorter than expected, leaving astronomers puzzled. Unlike Jupiter's centuries-old storm, Neptune's dark spots are transient. Hubble observations have revealed that they appear, shift latitude, and then dissipate within a few years. Sometimes, smaller companion storms seem to form alongside them, as if the planet's atmosphere is playing out an unpredictable drama. Why do Neptune's storms behave so differently? The planet is an ice giant, with an atmosphere dominated by hydrogen, helium, and methane, yet its dynamics remain poorly understood. Winds on Neptune are the fastest recorded in the solar system, reaching over 2,000 kilometers per hour, and these dark spots may be products of violent, chaotic flows deep within its atmosphere. But their transient nature remains unexplained. Some theories suggest they form from instabilities at great depths, only to be erased by turbulent layers above. Others propose that Neptune's internal heat, greater than the energy it receives from the Sun, fuels storm systems that flicker in and out of existence. The dark spots remind us that even in our own solar system, familiar planets harbor mysteries that defy understanding. Neptune, cold and distant, still whispers secrets through storms that appear and vanish like cosmic phantoms. In the first few minutes after the Big Bang, the universe was a seething plasma of particles. As it cooled, protons and neutrons fused into light elements, hydrogen, helium, and trace amounts of lithium. The predicted ratios of these elements, based on well-established physics, match observations with striking accuracy, except for lithium. When astronomers study ancient stars, the lithium they contain is only about a third of what theory predicts. This discrepancy, known as the lithium problem, has persisted for decades. Something in the early universe either destroyed lithium, prevented it from forming, or altered its abundance in ways we cannot explain. Some propose that new physics may have been at play during the first minutes of creation, involving exotic particles or unknown interactions. Others suggest stellar processes may have depleted lithium in old stars, though this too fails to explain the consistency of the discrepancy across different populations. The lithium problem is more than a missing chemical, it is a crack in the otherwise successful model of Big Bang nucleosynthesis. If solved, it could reveal new insights into the earliest seconds of the universe, or even point toward physics beyond the standard model. Until then, lithium stands as a small element with a massive mystery. One of the most profound unsolved discoveries is not about stars or galaxies, but about the universe itself. What is its shape? Does it curve back on itself like the surface of a sphere, stretch endlessly like a flat plane, or twist into something more exotic, beyond human intuition? Observations of the cosmic microwave background suggest that, to an extraordinary degree of precision, the universe is flat. Parallel lines remain parallel, and geometry behaves as expected. Yet even a slight curvature on the largest scales could change this conclusion, and measuring it with certainty is nearly impossible. If the universe is closed, it may eventually collapse back on itself in a big crunch. If it is open, expansion will continue forever, stretching galaxies apart until only darkness remains. A flat universe suggests a delicate balance, but why this balance exists at all is a mystery in itself. Some theorists suggest that inflation, the rapid expansion after the Big Bang, stretched the cosmos to near-perfect flatness. Others wonder if the shape is more complex, perhaps a torus or higher dimensional construct that only appears flat within our limited perspective. The true geometry of the universe remains unknown, hidden beyond the cosmic horizon. Every observation is a glimpse into its possible form, but the complete answer lies in realms forever out of reach. The shape of the universe is not just a mathematical question, it is a question about the destiny of all that exists. In 2017, astronomers detected a strange object hurtling through the solar system. Unlike comets or asteroids bound to the Sun, this body, later named Oumuamua, was on a hyperbolic trajectory, meaning it had come from interstellar space. It was the first confirmed visitor from beyond our solar system. At first glance, it resembled a typical asteroid. But as more observations were gathered, its properties grew increasingly unusual. It was extremely elongated, perhaps cigar-shaped or pancake-like, with a brightness that changed dramatically as it tumbled through space. Even stranger, it accelerated slightly as it moved away from the Sun, behavior normally seen in comets as gases sublimate and provide a gentle push. Yet Oumuamua showed no tail, no coma, no visible signs of outgassing. These anomalies ignited debate. Some proposed it was a fragment of a larger body, its surface hardened by cosmic radiation. Others suggested exotic ices sublimating invisibly could explain its motion. More speculative theories even raised the possibility of an artificial origin, perhaps a fragment of alien technology or a discarded probe. Whatever it was, Oumuamua passed too quickly for detailed study, vanishing into the dark beyond before telescopes could capture its secrets. Its brief visit left behind more questions than answers. Future interstellar objects will surely pass through, but the first visitor remains an unresolved mystery, a messenger from another star system that slipped quietly through our cosmic neighborhood. At Saturn's North Pole lies a phenomenon unlike anything else in the solar system, a vast hexagonal storm. First revealed by the Voyager spacecraft in the 1980s and later imaged in detail by Cassini, this immense jet stream forms a nearly perfect six-sided shape, locked in place around the pole. Each side of the hexagon is longer than the diameter of Earth. How such a structure can persist for decades remains an enigma. On Earth, jet streams meander and shift with atmospheric dynamics, yet Saturn's hexagon remains stable, rotating with the planet. Some models suggest that it arises from standing wave patterns in Saturn's atmosphere, where differential rotation creates the polygonal shape. Laboratory experiments with fluids have reproduced hexagonal vortices under certain conditions, offering tantalizing hints. Still, the scale and persistence of Saturn's hexagon make it unique. Beneath the swirling clouds, Saturn's interior dynamics remain hidden, and the connection between deep flows and the visible atmosphere is uncertain. Cassini even observed seasonal changes in the hexagon's color, shifting from bluish hues to golden tones as sunlight returned to the northern hemisphere. The hexagon stands as a reminder that even within our solar system, planets harbor features that defy easy explanation. A storm sculpted into geometric perfection, spinning endlessly above Saturn's pole, is one of the strangest atmospheric mysteries ever observed. In the standard model of cosmology, galaxies form within halos of dark matter. Simulations predict that large galaxies like the Milky Way should be surrounded by hundreds, if not thousands, of smaller satellite galaxies, tiny companions orbiting like sparks around a flame. Yet when astronomers look to the skies, they find far fewer. This discrepancy is known as the missing satellites problem. The Milky Way, for example, hosts only a few dozen known dwarf galaxies, far short of theoretical predictions. Where are the missing companions? Have they failed to form, or are they simply invisible to our instruments? One possibility is that many satellites exist as dark galaxies, containing dark matter but little to no stars, making them nearly impossible to detect. Another theory suggests that stellar feedback, supernova explosions and stellar winds, blows gas out of small galaxies, preventing star formation. Still others argue that observational limits hide faint companions, and deeper surveys may yet reveal more. In recent years, ultra-faint dwarf galaxies have indeed been discovered, hinting that some of the missing satellites may slowly be coming into view. But the gap between prediction and observation remains significant. The missing satellites problem continues to challenge our understanding of galaxy formation, raising the question of whether the models themselves require revision. Between the filaments of the cosmic web lie enormous voids, regions of space almost entirely empty of galaxies, stars, or even gas. Some of these voids stretch hundreds of millions of light years across, making them among the largest known structures in the universe, defined not by presence, but by absence. One of the most striking is the Boötes void, discovered in the 1980s. Spanning 330 million light-years, it contains only a few dozen galaxies, where thousands would normally be expected. Its sheer emptiness raises questions about how such vast regions formed. Did matter flow outward during cosmic expansion, leaving behind deserts in space? Or do these voids represent anomalies in the distribution of dark matter and dark energy? Voids are not completely empty, they contain faint whispers of matter and the occasional lonely galaxy. Yet they remain zones of cosmic silence, far removed from the bustling filaments where galaxies cluster. If life exists elsewhere, the odds of it arising in such desolate expanses are vanishingly small, making voids natural dead zones in the search for civilizations. Still, they hold importance. Light passing through voids is subtly altered, leaving imprints that cosmologists use to probe the nature of dark energy and the geometry of the universe. These silent regions may one day provide answers to some of the deepest mysteries. For now, they remain vast gulfs of nothingness, enigmatic and haunting reminders that most of the cosmos is not filled with galaxies, but with emptiness itself. Spacecraft traveling near Earth sometimes experience small but unexplained changes in speed during gravity-assist maneuvers. These flybys are used to slingshot probes toward distant planets, carefully calculated using precise models of gravity and orbital mechanics. Yet in several missions, including Galileo, NEA, and Rosetta, the spacecraft emerged from Earth flybys with slight velocity discrepancies that cannot be fully explained. The effect is tiny, measured in millimeters per second, but it is real. Instruments detect subtle deviations from predicted paths, as if an unknown influence nudged the spacecraft. Engineers have combed through possible explanations: atmospheric drag, tidal effects, radiation pressure, and thermal emissions. None fully account for the pattern. Some researchers suggest the anomaly may hint at overlooked details in how Earth's rotation interacts with relativistic effects. Others propose modifications to gravity at very small scales, or even exotic interactions with dark matter near Earth. Though small, the flyby anomaly is significant. Space navigation depends on extreme precision, and even minor deviations raise fundamental questions. If the effect persists and cannot be explained, it may point toward gaps in our understanding of motion in curved space-time. Each unexplained nudge reminds us that even close to home, the universe can behave in unexpected ways. Venus, Earth's twin in size and mass, hides beneath thick clouds of sulfuric acid and carbon dioxide. Its surface is a furnace, hotter than Mercury despite being farther from the Sun. Yet it is in its atmosphere that one of the most puzzling discoveries has emerged. In 2020, researchers reported possible detection of phosphine gas high in Venus's clouds. On Earth, phosphine is associated with biological processes or with artificial production. Its presence on Venus, where conditions are hostile to life, sparked intense debate. Could microbial life exist in the temperate cloud layers, shielded from the scorching surface below? Or might unknown chemical processes be producing the gas without biology? Subsequent studies have questioned the detection, with some arguing the signal may have been misinterpreted. Yet the possibility remains intriguing, highlighting how little is understood about Venus's atmospheric chemistry. Beyond phosphine, Venus displays other mysteries: superrotating winds that circle the planet in just 4 days, enigmatic lightning flashes, and hints of active volcanism shaping its clouds. Venus is often seen as a warning of what happens when a planet undergoes runaway greenhouse effects. But its unexplained atmospheric phenomena keep it at the forefront of planetary science. Beneath its golden shroud, Venus may hold answers not only to its own story, but to the broader question of how habitable worlds can evolve, or collapse, under the forces of nature. Across the universe, magnetic fields weave through galaxies, clusters, and even the vast intergalactic medium. Though invisible, they shape cosmic evolution, guiding charged particles, influencing star formation, and affecting the dynamics of galaxies. Yet their origin remains one of the great unsolved discoveries. Magnetic fields in galaxies appear coherent on scales of tens of thousands of light years. How could such vast, ordered structures arise? One theory suggests that tiny seed fields formed in the early universe, perhaps during phase transitions after the Big Bang. Over billions of years, turbulence and rotation within galaxies could have amplified them to the strengths observed today. Another possibility is that primordial plasma instabilities generated the fields during cosmic inflation, embedding magnetism into the fabric of space itself. If true, magnetic fields are not secondary effects, but fundamental features of the universe. Despite decades of study, their full origin remains unknown. Observations of distant quasars and polarized light reveal magnetism stretching across intergalactic voids, hinting that fields pervade all of space. Yet no consensus exists on how they began or why they align across such immense distances. Cosmic magnetism remains a quiet enigma. It cannot be seen directly, only inferred through its influence. But it is everywhere, silently threading the cosmos, binding together galaxies and shaping their destinies, while its true beginnings remain hidden in time's earliest moments. In recent years, astronomers have discovered galaxies so faint and spread out that they challenge definitions of what a galaxy even is. These ultra-diffuse galaxies contain as few stars as dwarf galaxies, yet stretch across diameters comparable to the Milky Way. Their ghostly forms float almost invisibly in clusters, barely detectable against the darkness. The most puzzling aspect is their apparent lack, or excess, of dark matter. Some ultra-diffuse galaxies appear dominated by dark matter, their stars held together only by invisible mass. Others, surprisingly, seem to contain little or no dark matter at all, defying models that rely on it for galaxy formation. How can such galaxies exist? Some theories suggest tidal interactions, where larger galaxies strip material and reshape them into diffuse remnants. Others argue that they may have formed in regions of the universe with unusual dark matter distributions. Their mere existence forces astronomers to reconsider how galaxies grow and evolve. Are they failed giants, never able to form stars efficiently? Or are they relics of ancient collisions, survivors of cosmic events that erased their structure? Ultra-diffuse galaxies remain difficult to study due to their faintness, but their strange properties may hold clues about dark matter itself. They are ghosts of the universe, giant yet fragile, luminous yet nearly invisible, haunting the boundaries of galactic science. Cosmic rays constantly rain upon Earth, bombarding the atmosphere with high-energy particles. Most are protons or atomic nuclei accelerated to near-light speeds. Yet despite a century of study, their exact origins remain uncertain. Supernova remnants are thought to be prime sources. Shockwaves from exploding stars can accelerate particles to tremendous speeds, scattering them across the galaxy. But for the highest energy cosmic rays, even supernovae may not suffice. Their energies exceed what such explosions should produce, suggesting even more powerful accelerators at work. Candidates include active galactic nuclei, where supermassive black holes fling jets of plasma into intergalactic space, or gamma-ray bursts, the most powerful known explosions. But when astronomers trace the arrival directions of cosmic rays, they find no clear alignment with such sources. Magnetic fields across galaxies bend their paths, obscuring their origins like a cosmic smokescreen. Some researchers consider even more exotic sources: the decay of dark matter, the collapse of topological defects in spacetime, or remnants of physics from the early universe. Cosmic rays are both danger and tool. They threaten spacecraft electronics and astronauts, but also provide insights into processes far beyond laboratory reach. Their unsolved origins leave us with a puzzle. Somewhere in the universe, accelerators of unimaginable power are at work, yet remain unseen. In the late 20th century, astronomers mapping the cosmos uncovered structures so vast they defied imagination. One of the most striking is the Great Wall, a colossal filament of galaxies stretching over 500 million light-years. This immense structure is not alone. Other walls and superclusters have since been discovered, some spanning even larger distances. These discoveries challenge assumptions about cosmic uniformity. According to standard cosmology, matter on the largest scales should be evenly distributed. Yet the Great Wall suggests a universe sculpted into sheets and voids, as though galaxies were painted along the surface of invisible structures. How such vast alignments formed remains unclear. Gravity, dark matter, and cosmic expansion all play roles, but the sheer scale of these walls seems to exceed simple models. Did they arise naturally as filaments in the cosmic web, or do they hint at deeper forces guiding the clustering of galaxies? Some structures, like the Hercules Corona Borealis Great Wall, appear so large that they may even challenge the cosmological principle, the assumption that the universe is homogeneous on the grandest scales. If true, the universe may not be as uniform as once believed, but instead woven into immense, interconnected tapestries of matter. the Great Wall of Galaxies stands as one of the largest unsolved discoveries in cosmology, a monument written in stars and clusters, stretching across distances beyond human comprehension. While galaxies generally drift apart due to cosmic expansion, studies of galaxy clusters have revealed something unexpected, a large-scale motion toward a particular region of the sky. This phenomenon, dubbed dark flow, suggests that clusters are being pulled by an unseen influence outside the observable universe. Measurements using the cosmic microwave background indicate that hundreds of clusters, across billions of light-years, share a coherent motion that standard cosmology cannot easily explain. The direction of this flow lies toward a point near the constellations Centaurus and Hydra, as if something beyond the cosmic horizon exerts a gravitational tug. What could cause such motion? Some propose that massive structures, invisible to us because they lie beyond the observable edge, are pulling matter toward them. Others speculate that dark flow may hint at new physics, perhaps interactions with regions of a larger multiverse, or imprints left by conditions prior to the Big Bang. Though later studies have debated the strength of the evidence, the possibility remains open. If real, dark flow suggests that our observable cosmos is not self-contained, but influenced by realms we cannot see. It would mean that beyond the edge of visibility, the universe continues in ways that alter even the motions of galaxies we can observe. Dark flow is both unsettling and profound. It whispers of forces outside our reach, tugging at galaxies like unseen hands across the void. The early universe, after the Big Bang, was a dark place. For hundreds of millions of years, no stars or galaxies yet shone. This period, known as the Cosmic Dark Ages, ended when the first stars ignited, a time called the Cosmic Dawn. Yet the details of this transformation remain shrouded in mystery. When exactly did the first stars form? What processes gathered the first clouds of hydrogen into luminous beacons? And how did these stars reionize the universe, clearing the cosmic fog so light could travel freely? Observations with powerful telescopes like the James Webb Space Telescope are beginning to probe this epoch, revealing galaxies that formed astonishingly early, perhaps earlier than theory predicts. Some appear massive and structured, suggesting that galaxy formation began faster than models allow. This raises deep questions. Did the laws of physics operate differently in the early universe? Were dark matter and dark energy influencing star birth in unexpected ways? Or have we underestimated the efficiency with which matter can collapse into stars? The cosmic dawn remains one of the last great frontiers in observational astronomy. It is the story of the first light, the moment when darkness gave way to brilliance, and the universe became illuminated. Yet the details of this grand awakening remain unsolved, a missing chapter in the history of everything. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies and dwarf planets. For decades, astronomers expected its population to taper off gradually with distance from the Sun. Yet surveys revealed something startling. At around 50 astronomical units, the number of objects drops dramatically, as though the solar system ends abruptly. This sudden decline is called the Kuiper Cliff. Why should such a boundary exist? No clear physical mechanism explains why small icy worlds should cease to form or survive beyond this distance. Some suggest that the gravitational influence of a yet undiscovered planet, sometimes called Planet 9, could have sculpted the outer belt, ejecting or scattering objects. Others propose that interactions with passing stars in the solar system's infancy stripped away material from the outer regions. Another possibility is that the distribution of primordial material simply ended near this distance, setting a natural edge to the solar system's icy reservoir. But evidence remains incomplete, and new surveys continue to find objects that blur the boundaries. The Kuiper Cliff remains a reminder that our own cosmic neighborhood is still filled with surprises. The drop-off in worlds at the edge of the solar system suggests hidden influences and processes we have yet to uncover. Beyond the cliff, the Sun's dominion fades, and the unknown begins. The universe as we know it is made of matter, atoms, protons, and neutrons. Yet physics tells us that matter and antimatter should have been created in equal amounts during the Big Bang. When matter and antimatter meet, they annihilate, producing pure energy. If the universe began with symmetry, then both should have destroyed each other, leaving nothing but radiation. And yet, matter remains, while antimatter is almost absent. This imbalance, known as the baryon asymmetry problem, is one of the deepest mysteries of cosmology. Why does matter exist at all? Why was there a slight excess of matter over antimatter, enough to seed galaxies, stars, and life? Theories attempt to explain it through subtle violations of symmetry in particle physics. Certain processes, known as CP violation, allow matter and antimatter to behave slightly differently. But the observed violations in experiments are not enough to explain the vast imbalance of the universe. Some suggest that new, undiscovered particles or forces may have tilted the scales. If the mystery is solved, it will answer not only why the cosmos exists in its current form, but why there is something rather than nothing. The baryon asymmetry is not merely a technical detail, it is the reason galaxies shine, planets orbit, and observers ponder their place in existence. While Tabby's star gained fame for its bizarre dimming, another puzzle lies in its infrared signature. Normally, if large amounts of dust orbit a star and cause irregular flickering, astronomers would expect to detect warm infrared radiation emitted by the dust. Yet when KIC 846-2852 was studied, this excess infrared emission was conspicuously absent. This contradiction deepens the star's mystery. If not dust, what else could be responsible for the unusual light curves? Comet swarms have been proposed, though the scale of material needed makes this unlikely. Another idea suggests fragmented planetary debris or collisions, but such events should leave detectable heat signatures. The lack of infrared radiation has fueled speculation about megastructures, vast artificial constructs capable of blocking starlight without producing excess heat. While such ideas remain speculative and controversial, they highlight how unusual the observations are. Subsequent studies have offered more nuanced explanations, such as fine dust particles distributed in ways that minimize infrared emission. Yet none are fully conclusive. The star remains a subject of fascination because it defies simple classification. It may one day turn out to have a natural explanation, but until then, KIC 846-2852 is a reminder that the universe can surprise even the most experienced observers with enigmas that resist resolution. The cosmic microwave background, CMB, is often described as the most perfect evidence of the Big Bang, a nearly uniform glow of radiation filling the universe. Yet within its smoothness lie peculiar anomalies that remain unexplained. These include the axis of evil, a strange alignment of temperature fluctuations, and unexpected asymmetries between hemispheres of the sky. Standard cosmology predicts that the CMB should display random variations, distributed evenly in all directions. Instead, these anomalies suggest subtle patterns on scales too large to be chance alone. Why should one hemisphere of the sky look statistically different from the other? Why should fluctuations align along a specific axis? Some propose that these features are statistical flukes, amplified by human interpretation. Others argue that they may point to new physics, imprints of cosmic inflation, signatures of collisions with other universes, or evidence that the universe is not as isotropic as once assumed. The CMB anomalies continue to challenge the simplest picture of the early cosmos. If confirmed as real, they could force a re-evaluation of our models of the universe's birth. For now, they remain strange irregularities, whispers of something deeper hidden in the afterglow of creation. When astronomers study galaxies, they measure how stars orbit around their centers. By Newtonian expectations, stars farther from the core should orbit more slowly, just as planets in our solar system do. Yet observations reveal the opposite. Stars in the outer arms move just as fast as those near the center. These flat rotation curves cannot be explained by visible matter alone. This discovery was one of the strongest pieces of evidence for dark matter. If galaxies are surrounded by vast, invisible halos of unseen mass, the extra gravity would explain why stars remain bound and orbit with such speeds. Yet despite decades of searching, dark matter itself has never been directly detected. Alternative theories propose modifications to the laws of gravity, such as modified Newtonian dynamics, which alters how gravity behaves at very low accelerations. While such models can fit some galactic data, they struggle to explain the full range of cosmological observations. The flatness of galaxy rotation curves remains a profound puzzle. Whether caused by exotic matter or new laws of physics, the discrepancy highlights the limits of current understanding. Every spiral galaxy, spinning gracefully in the night sky, carries within it a silent question: what unseen force holds it? Red dwarf stars are the most common in the galaxy, small and cool compared to stars like the Sun. Their habitable zones, the regions where liquid water could exist, lie much closer to the star, meaning planets orbit tightly in fast, short years. This abundance suggests that many potentially habitable worlds may orbit red dwarfs. Yet questions linger about whether such planets could truly host life. Red dwarfs are highly active, often unleashing powerful flares that bombard nearby planets with radiation. A planet close enough for warmth may be tidally locked, with one side in perpetual daylight and the other in eternal night. Can such conditions support stable climates, oceans, and atmospheres? Some models suggest that thick atmospheres or oceans could redistribute heat, allowing habitability even on tidally locked worlds. Others argue that magnetic fields could shield against stellar flares. Yet uncertainty remains. Would such worlds be barren deserts, scorched by stellar outbursts, or could they nurture life adapted to alien cycles of light and dark? Because red dwarfs are so common, answering this question may determine whether life is likely widespread in the galaxy or extraordinarily rare. The enigma of red dwarf habitability sits at the crossroads of astrophysics and biology, a mystery that could redefine humanity's understanding of its place among the stars. For centuries, astronomers have charted the solar system with increasing precision, uncovering new worlds from Uranus to Pluto. Yet in recent years, subtle patterns in the orbits of distant icy bodies have hinted at the presence of something more, an unseen giant lurking in the dark. This hypothetical world, dubbed Planet 9, may be 10 times the mass of Earth, orbiting far beyond Neptune in an elongated path that takes thousands of years to complete. Evidence for Planet 9 comes from the unusual clustering of objects in the Kuiper belt. Instead of orbiting randomly, their trajectories seem aligned, as though shepherded by the gravitational pull of a massive, hidden body. Computer models suggest that a distant planet could explain these alignments, along with other anomalies in the outer solar system. But no direct detection has yet been made. If it exists, Planet 9 would be faint, cold, and difficult to spot, lost in the vastness of the sky. Powerful surveys are underway to find it, scanning the remote reaches where its slow orbit might reveal a subtle motion against the stars. If discovered, Planet 9 would reshape our understanding of the solar system's architecture and history. Was it born alongside the other planets, or captured from interstellar space? Until it is found, or definitively ruled out, Planet 9 remains one of the most tantalizing unsolved mysteries at the edge of our cosmic neighborhood. At the hearts of galaxies lie supermassive black holes, millions to billions of times more massive than the Sun. Their existence is not in doubt. Telescopes have observed their gravitational influence, their jets, and even the shadow of one. But how did such titans form so early in cosmic history? Some galaxies less than 1 billion years after the Big Bang already host black holes with enormous masses. Growing from the collapse of ordinary stars seems too slow. Even with steady feeding, they should not have reached such sizes so quickly. This puzzle has led to the idea of seeds, massive precursors that allowed rapid growth. But what were these seeds? Did they form from the direct collapse of enormous primordial gas clouds, bypassing normal star formation? Or were they the remnants of exotic stars, thousands of times more massive than today's? Another possibility is that dense stellar clusters merged into gravitational giants, collapsing under their own weight. Understanding the origins of supermassive black holes is key to understanding galaxies themselves, for their growth appears intertwined. Until the mystery of the seeds is solved, the birth story of both galaxies and their central black holes remains incomplete, a cosmic riddle at the very heart of structure formation. Space between the stars is not truly empty. It contains gas, dust, and faint plasma, collectively called the interstellar medium. Yet the amount and nature of this material is far stranger than once believed. Astronomers studying starlight find that it is scattered, reddened, and polarized in ways that reveal hidden complexity in this invisible medium. Even stranger are phenomena like diffuse interstellar bands, mysterious absorption features in the spectra of stars, first detected nearly a century ago. These bands do not match any known molecule or dust grain, leaving their carriers unidentified. Thousands of such features exist, suggesting a vast array of unknown chemistry drifting between the stars. Some propose complex carbon molecules, perhaps even precursors to life, as possible carriers. Others suggest exotic states of matter, forged in supernovae and scattered across space. Despite decades of laboratory work and observation, the puzzle remains unresolved. The interstellar medium is not just a backdrop, it is the raw material from which new stars and planets form. Hidden within its dust and gas may lie answers to questions about cosmic evolution and the origins of life. Until the unseen matter between the stars is fully understood, it remains one of the most enduring unsolved discoveries of the universe. Jupiter's Great Red Spot has fascinated astronomers for centuries. First observed in the 1600s, this colossal storm is larger than Earth, swirling in Jupiter's atmosphere with winds exceeding 400 kilometers per hour. Yet despite centuries of observation, its true nature remains a puzzle. Why has the storm persisted for so long when terrestrial storms dissipate within weeks? Some models suggest that Jupiter's lack of solid surface allows storms to endure indefinitely, while others propose that deep atmospheric layers feed energy into the vortex. Recent spacecraft observations reveal that the storm extends deep into the atmosphere, perhaps hundreds of kilometers, hinting at complex internal dynamics. Another mystery is its color. The reddish hue may result from complex chemical reactions in Jupiter's upper atmosphere, triggered by ultraviolet radiation. Yet the exact compounds remain uncertain. Laboratory simulations produce some candidates, but none perfectly match the shade observed from space. In recent decades, the Great Red Spot has been shrinking, raising questions about whether it is slowly fading. Will it vanish entirely, leaving only smaller vortices in its place? Or will it stabilize and endure for centuries to come? The storm remains one of the solar system's most iconic features, a monument to planetary weather on a scale far beyond Earth. Yet even after centuries of study, it continues to defy full explanation, a reminder that familiar sights can still conceal deep mysteries. Pulsars, rapidly spinning neutron stars, emit beams of radiation that sweep across space like cosmic lighthouses. Their pulses are so precise that they rival atomic clocks, allowing astronomers to use them as natural timekeepers. Yet within this precision lie anomalies that raise profound questions. Some pulsars suddenly change their rotation rate in events known as glitches. These abrupt jumps suggest internal processes, perhaps involving superfluid layers within the star's crust. But the exact mechanisms remain uncertain, hidden within matter at densities impossible to replicate on Earth. Even stranger are timing irregularities in certain pulsars that defy predictions. Millisecond pulsars, for example, sometimes show subtle drifts that hint at unknown companions, exotic matter interactions, or even ripples in spacetime caused by gravitational waves. Networks of pulsars are now being monitored as detectors for these cosmic ripples, potentially opening new windows on the universe. Pulsars are also linked to mysteries like fast radio bursts, with some theories suggesting that magnetized neutron stars may play a role. Their signals, at once precise and erratic, remind astronomers that these objects are not fully understood. Each irregularity in pulsar timing is a clue to physics under extreme conditions. These stellar remnants, spinning with relentless rhythm, are not only remnants of dead stars but laboratories of the unknown, broadcasting mysteries across the galaxy. The Big Bang theory explains the expansion of the universe, But another idea, cosmic inflation, was introduced to solve lingering puzzles. Inflation proposes that, in the first fraction of a second, the universe expanded faster than light, smoothing out irregularities and explaining why distant regions appear uniform. Yet inflation itself raises profound questions. What caused it? What field or particle drove this expansion? And why did it stop, allowing the universe to evolve into stars and galaxies? Different models of inflation exist, each proposing variations in how it began and ended. But no direct evidence has yet confirmed the exact mechanism. Some predictions of inflation include a background of gravitational waves imprinted on the cosmic microwave background. Detecting such signals would be strong evidence, yet searches have so far produced ambiguous results. Other cosmologists question inflation altogether, suggesting alternative theories like cyclic universes or modifications of space-time physics. If inflation is true, it may also imply the existence of a multiverse, where different regions inflated into separate universes with distinct properties. Inflation remains a powerful idea, explaining much about cosmic structure, yet its foundations rest on the unknown. It is a theory both elegant and unsettling, an unsolved chapter in the story of creation. The largest structures in the universe are not galaxies or clusters, but the voids, immense regions almost empty of matter. These cosmic deserts stretch across hundreds of millions of light-years, shaping the web-like distribution of galaxies. Yet their influence may extend beyond simple absence. One of the most intriguing possibilities links voids to the cold spot in the cosmic microwave background. Some astronomers suggest that light traveling through a giant void could lose energy, leaving behind the unusually cool region observed in the CMB. Known as the integrated Sachs-Wolf effect, this explanation fits some models but struggles to fully account for the cold spot's size and depth. If voids do cause such anomalies, they may play a more active role in shaping cosmic observations than once thought. But the exact processes remain unclear. Are voids simply regions where matter failed to gather, or do they represent deeper imbalances in the fabric of the universe? Voids also challenge models of dark matter and dark energy. Their growth and distribution reflect how cosmic expansion unfolds, making them sensitive probes of fundamental physics. Yet mapping them in detail remains difficult, requiring vast surveys of galaxies to trace where matter is not. These immense, silent gaps remind us that the universe is defined as much by emptiness as by presence. Voids are not nothing, they are active players in cosmic evolution, though their full role is still unsolved. Saturn's rings are among the most beautiful sights in the solar system, yet their origin and age remain mysterious. Composed mostly of ice, with fragments ranging from tiny grains to house-sized boulders, the rings stretch thousands of kilometers yet are astonishingly thin. One mystery is their age. Some studies suggest the rings are relatively young, perhaps only 100 million years old, formed during the age of dinosaurs on Earth. If true, they may have arisen from the breakup of a moon or comet torn apart by Saturn's gravity. Other models suggest the rings could be primordial, remnants of material left over from Saturn's formation. The rings are also eroding. Micrometeorite bombardment and gravitational interactions gradually darken and disperse the material, meaning they may one day vanish. Cassini's final dives through the rings revealed unexpected complexity, including ring rain falling into Saturn's atmosphere and mysterious wave patterns shaped by hidden moonlets. Why Saturn alone possesses such grand rings, while Jupiter, Uranus, and Neptune have only faint bands, is another unsolved question. Are Saturn's rings unique in origin, or are they simply caught in a fleeting stage of planetary evolution? Saturn's rings are both transient and timeless, an unsolved wonder circling in silence, reminding us that even the most familiar sights may conceal deep mysteries. Galaxies are not static islands in space. They interact, collide, and sometimes consume one another in acts of cosmic cannibalism. Evidence for this lies in streams of stars torn from smaller galaxies, stretched across the sky like scars of ancient encounters. The Milky Way itself is consuming the Sagittarius dwarf galaxy, pulling it apart piece by piece. but some observations reveal puzzling details. Certain galaxies appear to have absorbed others yet show little disruption, as though the merger left them largely intact. Others display unusual star populations or irregular shapes that do not fit standard models of collisions. Even more mysterious are ultra-compact dwarf galaxies, thought to be remnants of larger galaxies stripped of their outer layers. Are these survivors of galactic cannibalism, or did they form through entirely different processes? Cannibalism also plays a role in galaxy growth. Supermassive black holes may feast on material delivered by mergers, powering quasars and shaping galactic evolution. Yet how often these events occur, and how they influence cosmic history, remains unresolved. Every galaxy carries a hidden record of past meals, encoded in its stars and motions. Yet the details of these violent interactions, how they begin, how they end, and how they shape the universe, remain an unsolved discovery, written across the night sky in patterns we are only beginning to decipher. While galaxy rotation curves reveal dark matter on individual scales, even larger mysteries appear when galaxies are studied in groups and clusters. Observations suggest that the motions of galaxies within clusters do not match predictions based solely on visible matter. Something more massive must be binding them together. Dark matter is the leading explanation, forming halos that stretch far beyond the visible edges of galaxies. Yet even with dark matter included, inconsistencies remain. Some clusters exhibit motions and gravitational effects that appear too strong, hinting at missing mass or misunderstood dynamics. The famous Bullet cluster, where two clusters collided, provided evidence that dark matter exists separately from normal matter, but even this raises questions about its true properties. Alternative ideas propose modifications to gravity itself, challenging one of the most fundamental forces in physics. Could gravity behave differently on cosmic scales than it does in solar systems? If so, our very understanding of the universe's architecture would require rewriting. On the grandest scales, galaxies flow like currents in a vast cosmic ocean, their motions hinting at hidden depths beneath the surface. Whether explained by unseen matter, altered laws, or something more exotic, galactic motion remains an unsolved signature of forces beyond our grasp. Saturn's icy moon Enceladus, only 500 kilometers wide, should have been a frozen, inactive world. Instead, it astonished astronomers by erupting with towering plumes of water vapor from cracks near its south pole. These geysers, discovered by the Cassini spacecraft, spray into space and replenish Saturn's E-ring, revealing a hidden ocean beneath the icy crust. The presence of liquid water so far from the Sun is itself a mystery. Tidal forces from Saturn's gravity may generate enough heat to keep the ocean liquid, but the intensity and persistence of activity suggest something more complex. Cassini detected organic molecules, salts, and even hints of hydrothermal activity in the plumes, processes that, on Earth, are linked to life. Could Enceladus harbor living ecosystems beneath its frozen shell? If so, it would revolutionize the search for life beyond Earth. But many questions remain unsolved. How deep is the ocean? How long has it existed? And how does a small moon sustain such dynamic energy over billions of years? Enceladus is both a scientific puzzle and a beacon of possibility. Its icy geysers whisper that even tiny, distant worlds can harbor secrets far greater than expected, perhaps even answers to one of humanity's most profound questions. Quasars shine as the brightest objects in the universe, their light outshining entire galaxies. Powered by supermassive black holes devouring matter, they release energy through jets and radiation on unimaginable scales. But the exact mechanics of how they generate such extraordinary luminosity remain incompletely understood. As matter falls into a black hole's accretion disk, it heats to millions of degrees, emitting torrents of radiation. Yet the efficiency of this process seems too high, suggesting mechanisms beyond simple friction and heating. Magnetic fields may funnel energy into colossal jets that pierce intergalactic space, but how these fields remain stable is still debated. Some quasars flicker in brightness, varying on timescales far shorter than expected, challenging models of their inner structures. Others seem to switch on and off across cosmic timescales, leaving behind dormant black holes awaiting new fuel. Quasars also serve as probes of the distant universe, their light passing through intervening gas and revealing conditions billions of years ago. But the question of their internal engines, the true source of their staggering energy output, remains unresolved. They are both lighthouses and mysteries, beacons from the early universe whose brilliance continues to outpace understanding. Each quasar is a puzzle, blazing across the night with power still unexplained. The discovery that the universe's expansion is accelerating, driven by dark energy, raised profound questions not only about the present but also about the future. If acceleration continues indefinitely, galaxies will drift farther and farther apart until, billions of years from now, only local clusters remain visible. But alternative outcomes remain possible, and the true destiny of the cosmos is still unsolved. One scenario is the Big Rip. If dark energy grows stronger with time, it could eventually overcome every force in nature, tearing galaxies, stars, planets, and even atoms apart. In this vision, the universe ends not with a collapse, but with disintegration at every scale. Another possibility is the heat death. In this slow fade, galaxies move beyond each other's horizons, stars burn out, and black holes evaporate over unimaginable timescales. The cosmos becomes dark and cold, an endless expanse of entropy. Some models suggest dark energy could decay or reverse, leading to a big crunch, where expansion halts and the universe collapses back into itself. Others propose oscillating cycles of expansion and contraction, a cosmic heartbeat without end. Which outcome awaits depends on the true nature of dark energy, a force still shrouded in mystery. The universe's fate remains unwritten, one of the greatest unsolved discoveries, waiting to be revealed by future observation. Among the planets of the solar system, Uranus is an oddity. Unlike its neighbors, it rotates on its side, tilted at nearly 98 degrees. Its poles point almost directly toward the Sun, leading to extreme seasonal cycles where one hemisphere can bask in sunlight for decades while the other lies in darkness. How did Uranus end up this way? The leading theory suggests a massive collision early in its history, perhaps with an Earth-sized body, knocked it onto its side. Such an impact could also explain its faint ring system and unusual magnetic field, which is tilted and offset from the planet's center. Yet mysteries remain. Uranus radiates little internal heat compared to other giant planets, raising questions about whether the same impact that toppled it also disrupted its internal structure. Its atmosphere, filled with methane, produces a striking blue-green color, but the dynamics of its weather patterns are still poorly understood. The tilt of Uranus is more than a curiosity, it reshapes the planet's climate, magnetic environment, and evolution. If collisions of this scale were common in the early solar system, they may also have shaped Earth and other worlds in dramatic ways. Uranus remains a quiet, distant enigma, spinning sideways through the dark, holding secrets yet to be uncovered. Neutrinos are among the most abundant particles in the universe, streaming through every planet, star, and body of matter in endless numbers. Yet they interact so weakly with normal matter that trillions pass through each person every second unnoticed. Their ghostly nature makes them extraordinarily difficult to study, and despite decades of research, they remain one of the great unsolved discoveries. One mystery is their mass. Neutrinos were once thought to be massless, but experiments have shown that they oscillate between different flavors, a process that requires them to have tiny, non-zero masses. Yet the exact values remain unknown, as does the mechanism by which they acquire mass. Another puzzle is whether neutrinos are their own antiparticles. If so, they could provide clues to why matter dominates over antimatter in the universe. Their behavior may also tie into physics beyond the standard model, hinting at hidden particles or forces. Neutrinos also arrive from cosmic sources. Detectors buried deep underground have captured neutrinos from the Sun, from supernovae, and even from distant galaxies. Yet the highest energy neutrinos, detected by observatories like IceCube in Antarctica, defy explanation. Where are they born, And what engines could hurl them across the cosmos with such power? Neutrinos are both elusive and essential, woven into the very structure of the universe. They remain messengers from realms we cannot directly touch, carrying with them mysteries still unsolved. The observable universe is limited by the speed of light. Beyond about 46 billion light-years in any direction lies the cosmic horizon, the boundary of what we can see. Yet this horizon is not a physical wall, it is a consequence of time and distance, where light from farther regions has not had enough time to reach us. What lies beyond this horizon remains one of the greatest unsolved discoveries. Is the universe infinite, stretching endlessly with galaxies beyond counting? Or does it curve back on itself, looping into a closed structure where traveling far enough would bring one back to the starting point? The horizon also raises the horizon problem. Distant regions of the universe look nearly identical in temperature and structure, despite being too far apart to have ever interacted by the exchange of light. How did they achieve such uniformity? Cosmic inflation provides one explanation, suggesting that all regions were once connected before rapid expansion stretched them beyond contact. Yet inflation itself remains uncertain, leaving the true nature of the horizon unresolved. Beyond what we see may lie infinite space, exotic realms, or even domains with entirely different physical laws. The cosmic horizon is both a boundary and an invitation, a reminder that our vision of the universe is partial, and beyond it lies mystery. While the Sun is the closest and most studied star, it still holds unsolved mysteries, particularly in the high-energy particles it emits. Solar energetic particles, often released during flares or coronal mass ejections, sometimes reach energies far greater than models predict. These solar cosmic rays pose hazards to astronauts and spacecraft, yet their acceleration mechanisms are not fully understood. The Sun's magnetic fields twist and reconnect violently, releasing energy in explosive bursts. But why do some particles accelerate to extreme velocities, nearly reaching the speed of light, while others remain slower? Observations show variability that does not align neatly with existing theories. Adding to the puzzle is the solar corona, the outer atmosphere, which is vastly hotter than the Sun's surface. This coronal heating problem may tie directly to particle acceleration, but no definitive explanation exists. The Parker Solar Probe, currently flying closer to the Sun than any spacecraft in history, is beginning to measure these conditions directly, yet many questions remain unanswered. Understanding solar cosmic rays is not only a matter of safety for space travel but also a key to understanding how stars in general release energy into their surroundings. The Sun, familiar and constant in the sky, still harbors mysteries that remind us that even the nearest star is not fully understood. In 2015, detectors made history by recording gravitational waves, the ripples in spacetime predicted a century earlier. These signals, caused by colliding black holes or neutron stars, opened an entirely new way of observing the cosmos. Yet with this triumph came new mysteries. Some gravitational wave events are stronger or more unusual than expected. Black holes of unexpected masses, too heavy to form from normal stellar collapse, yet too light to be primordial giants, have been detected merging. Where did such black holes come from? Were they born from exotic processes in the early universe, or from repeated mergers within dense star clusters? Other events defy easy categorization. Signals may originate from sources still unknown, perhaps exotic stars, cosmic strings, or phenomena beyond current models. The catalogue of gravitational wave detections is growing, but with it comes the realization that the universe may host entirely new classes of events yet to be identified. Gravitational waves also raise the question of what lies beyond our current sensitivity. Faint ripples from the earliest moments after the Big Bang may still echo through the cosmos, carrying clues about inflation and the universe's birth. Detecting them would be one of the greatest achievements in science, but for now, their existence remains an unsolved mystery. Black holes are usually thought to form from the collapse of massive stars. But another possibility has long intrigued cosmologists. Primordial black holes, born in the earliest moments after the Big Bang. These hypothetical objects could have formed when extreme densities in the young universe caused regions of space to collapse directly under their own gravity. If they exist, primordial black holes might range in size from microscopic to millions of solar masses. Some could have evaporated quickly through Hawking radiation, while others might still wander the cosmos today, masquerading as dark matter. They might even serve as seeds for the supermassive black holes we observe at galactic centers. Searches for primordial black holes have probed their possible presence through gravitational lensing, gravitational waves, and the motions of stars, yet no conclusive evidence has emerged. Some models suggest that tiny primordial black holes could make up part of the dark matter halo surrounding galaxies, but others argue they would leave signatures we have not seen. If discovered, these ancient objects would be direct relics of the universe's infancy, fossils from a time when conditions were far more extreme than anything observed since. The mystery of primordial black holes remains unsolved, hovering between theory and detection, a possible key to both dark matter and cosmic origins. The rate at which the universe is expanding is measured by the Hubble constant. For decades, astronomers have refined this value, using observations of nearby stars and galaxies as well as measurements of the cosmic microwave background. Yet in recent years, a troubling discrepancy has emerged. Different methods give different answers. When measured using the local universe, Cepheid variables, supernovae, and galaxies, the Hubble constant appears higher. But when inferred from the early universe, using data from the Planck satellite's observations of the CMB, it appears lower. Both methods are precise, yet they disagree by a margin too large to dismiss as error. This Hubble tension suggests either unknown systematic problems in our measurements or new physics beyond the standard cosmological model. Could dark energy evolve differently than expected? Could hidden particles, like sterile neutrinos, have influenced the early universe's expansion? The disagreement continues to grow sharper as more precise measurements are made. If resolved, the Hubble tension could reshape our understanding of cosmic expansion and reveal new forces or components of the universe. Until then, the true rate of expansion remains one of the most pressing unsolved discoveries in modern cosmology. Among the strangest cosmic accelerators are blazars, active galaxies with supermassive black holes firing jets of plasma directly toward Earth. These jets emit radiation across the spectrum, from radio waves to gamma rays, and appear to accelerate particles to extreme energies. But the details remain elusive. High-energy neutrinos detected on Earth have been linked to blazars, suggesting that they are sources of cosmic rays. Yet the processes by which these jets accelerate particles remain uncertain. Magnetic fields, shock waves, and turbulence all play roles, but models struggle to reproduce the observed energies. Even stranger, some blazars flicker in brightness over hours or days, implying that their acceleration regions are compact, perhaps smaller than the solar system, yet capable of hurling particles across intergalactic space. How can such small regions unleash such immense power? The connection between blazars, cosmic rays, and neutrinos is one of the hottest questions in astrophysics today. Blazars are cosmic lighthouses, pointing directly at us, but their engines remain hidden behind layers of plasma and relativistic motion. Each detection brings us closer to answers, but the mystery of how these galactic powerhouses work remains unresolved. Dark energy is often described as the most mysterious discovery of all. It drives the accelerating expansion of the universe, yet it cannot be seen, touched, or measured directly. Unlike dark matter, which reveals itself through gravity, dark energy is inferred from the way galaxies move apart, defying gravity's pull. What is it? Some suggest it is the cosmological constant, a property of space itself that remains steady over time. Others propose it is a dynamic field, an evolving energy that changes as the universe ages. If so, its behavior could dictate the ultimate fate of the cosmos. Still more radical ideas suggest that dark energy is a sign our understanding of gravity is incomplete. Perhaps the equations we trust no longer apply on the largest scales, and the accelerating universe is not the work of a hidden energy, but of laws still unknown. Despite decades of study, no clear answers have emerged. Observations map the universe's expansion with exquisite precision, but the mechanism remains invisible. Dark energy is the silent architect of cosmic destiny, shaping the future of everything, yet its essence is unsolved, a riddle written into the very fabric of reality. Perhaps the most profound unsolved discovery is not about stars or galaxies, but about life. Does it exist elsewhere in the universe? The sheer number of planets, trillions upon trillions across billions of galaxies, suggests the possibility is strong. Yet despite decades of searching, no direct evidence has been found. Exoplanet surveys reveal worlds in habitable zones, some similar in size to Earth, orbiting stars near and far. Some may have oceans, atmospheres, and climates capable of sustaining biology. Yet whether they do is unknown. Closer to home, Mars shows evidence of ancient rivers and lakes. Europa and Enceladus harbor oceans beneath ice, warmed by tidal forces. Titan contains liquid methane lakes and complex organic chemistry. Any of these worlds could host life in forms familiar or alien. The silence of the skies remains haunting. Radio telescopes listen, probes explore, yet no signals or fossils have spoken. Is life truly rare, a fluke confined to Earth, or is it everywhere, waiting to be discovered in forms beyond recognition? Until the answer is found, the question lingers as one of the universe's greatest mysteries: are we alone? At the heart of every mystery lies one question deeper than the rest: why does anything exist at all? Physics describes how the universe evolves, how galaxies form, how stars burn, and how black holes devour. But it does not explain why there is a universe to begin with. Some suggest that the laws of physics demand existence, that nothingness is unstable and inevitably gives rise to something. Others propose multiverse models, where countless universes emerge, and we inhabit one where conditions allow observers to question it. Still others hold that the question itself lies beyond science, rooted in metaphysics or philosophy. Whatever the explanation, the fact remains that existence itself is the ultimate unsolved discovery. The cosmos stretches endlessly, filled with mysteries from dark matter to distant galaxies, yet all are secondary to the primal question: why is there a universe at all, and not nothing? It is the question that underpins every other puzzle, the silent foundation beneath the stars. Perhaps it has no answer. Perhaps the act of asking is itself the answer. From the smallest particles to the largest structures, from flickering stars to infinite voids, the universe is a tapestry of mysteries. Each unsolved discovery is both a barrier and an invitation, a reminder that knowledge expands only as far as curiosity dares to reach. We may never resolve all these enigmas. Dark matter may remain hidden, dark energy undefined, and the question of other lives unanswered. But perhaps that is the essence of exploration, not to arrive at certainty, but to journey ever deeper into wonder. The universe does not reveal itself easily. It keeps its secrets, layered in shadows and silence. Yet in every unanswered question lies the spark of discovery, the promise that tomorrow may reveal what today cannot. And so, the story of the cosmos is not finished. It continues, written in light and gravity, in whispers from the stars, and in the endless pursuit of understanding. For in the face of the unknown, one truth endures: the mysteries of the universe are not obstacles, but pathways, leading us always further into the infinite.